Now that we have seen the structure of binary trees and how to represent them using pointers and so on, I want to talk about a very important data structure known as the binary search trees. The binary search tree, or BST. Okay, so a BST is a binary tree, that satisfies a very important property. It satisfies the following property. For every node, the property is that for every node x in the binary search tree, if y is a node in the left subtree of x, then it must be that the key stored in y is smaller than or equal to the key stored in x. And if y is a node in the right subtree of x, then it must be that the key of the node y is greater than or equal to the key in the node x. Okay, so an example of a binary search tree, so I can have something like this. So if I put, like, let's say here 3, this node here on the left child of 3 must be a value smaller than or equal to 3. Let's say it's 1. All the nodes in the right subtree of 3 must have keys greater than or equal to 3. So for example, this could be 3 here, this could be 5, and this could be 9. But also notice that the same property applies for node 5. The left child of 5 is smaller than it, the right child of 5 is greater than it. And it's not just the children here. In this example, we have just one child, one left child, one right child of 5. But in general, all the nodes in the left subtree of 5 must be smaller than 5. All the nodes in the right subtree of 5 must have keys greater than or equal to 5 as well. Okay. Now, please keep in mind that this is a completely perfect binary search tree. There's nothing wrong with it. 1, 3, 9, 10, 15, 15. Okay, so this is a binary search tree that is storing values that are equal. Now, keep in mind that when we talk about sets, we usually don't allow the same element to appear more than once. Okay, so this is why in general, if we're talking about sets, we should not expect the same element to appear more than once. But in many applications, in reality, we need to allow the same element to appear more than once. For example, if I have the grades of different students and I want one node per grade, more than one student could have the same grade, so the keys will be the same, but then they will differ in a different field, the name of the student or the student ID. Okay, so usually these nodes have to differ in some key value. If they are all the same, then we are talking about a set that has multiple elements with the same values. So these are examples of a binary search trees, and I hope that you immediately see one of the problems with defining binary search trees like this, because later we will talk about specific types of binary search trees that allow us to avoid the example on the right, which what we call is a chain, because this is a tree that has a very, very big height. The height of a tree, which we usually denote by h of t. So if the tree is t, h of t is the height of the tree. The height of the tree is the length of the longest path from the root to a leaf in that tree. It's the length of a longest path from the root of t to a leaf of t. Okay, so if I look at this tree here, the height is 2, because this is the longest path, for example, here, and it has 2 edges in it. The length of a path is the number of edges on the path, not the number of nodes. So the height of this tree is 2. If I look at this tree on the right here, the height is 1, 2, 3, 4, 5. The height of this is 5. Okay, so here are 2 binary search trees with different heights. The height plays a big role in the efficiency of many of the operations that we define in binary search trees. Some operations have nothing to do with the height, but with the total number of nodes. So let's look at one of the operations that we are interested in when we look at the binary search trees. One of the operations is, let's say, traverse. We want to traverse a tree, traverse a binary search tree. Okay, so what does it mean to traverse a binary search tree? We want to visit all the nodes in that binary search tree. For example, one big uses of binary search tree is that if you visit the nodes in a very specific way and print the items in it, you will get a sorted list of all the elements in that tree. So if you think about this tree here, if we think about 5 and 3, 4, 1, and we have here, let's say 15, 12, 100, and 200. Then if we visit this tree in what we call in order, and print the nodes from this, that what we get is a sorted list of the keys in this binary tree. So if I do this algorithm in order, that takes as input a pointer to the root of that tree. So when we call it first, it is pointing to the root of the tree with key 5, and it is defined like this. So for example, if the node is not nil, okay, so we are not pointing to an empty tree, then call this function recursively on the left in order on x.left. So we are calling it on the left child, and then we say print the key of x, and then we call it recursively on the right child of x. This is the whole function in order. So if you run this on this given tree here, what's going to happen? Let's actually try to traverse it here. So I call it, and first I get to the node that has key 5. 5 is not nil. I call the function now recursively. I go to the node, I go to this node now, the node that has key 3. The node that has key 3 is not nil, therefore I go to the left. I go to 1, 1 is not nil, then I go to the left child of 1 is nil. Since it is nil, now we basically print the key of that node. So we print 1. We print 1. Then we come back. The recursive call goes back to the node that has key 3. It prints 3. Then it comes to the right child of 3, which is 4. It has no left and right children. It prints that key. Then we come back and go all the way now to the root, because now this is the node whose left subtree has already been visited. So now we print 5. Then from this node we come to this node with the key 15, but 15 is not nil. We go left. We go to 12. The left and right children of 12 are nil. We print 12. We come back here and print 15. Then we come to this one, 100. We try to go left. It has no children. We print 100. Then we come to this one. 200 has no left child, so we print 200. And it has no right child, and we are done. So if you look at the elements that were printed by this algorithm, it's the elements that are stored in the binary search tree in increasing order. If you think about the running time of this operation here, and you think about every node, every node is traversed a constant number of times, right? So this algorithm, if the tree has n nodes in it, then the running time of n order is O of n. In addition to n order, we also have We also have pre-order. In pre-order, the root x is visited, then the left of x, the left child of x, then the right child. So in pre-order, it's x, then x left, and then x right. In post-order, we do x left, x right, and then we do x. Okay, so notice that for in order, it was x left, visited first, then x right. Okay, so if you think about in order, x is in the middle. If you think about pre-order, x is pre everything else, so it's before the left and right. If you think about post-order, x is all the way on the right. It comes after everything. Okay, and again, as I said, the running time of this operation is O of n because we traverse this tree in O of n time. That's all we are doing. One other operation that's interesting, and it doesn't modify the tree in any way. We are not changing the tree in any way, is the operation of searching in a binary tree. Okay, so if I want to search in a binary tree, so imagine we have this binary tree, 15, 6, 7, 13, 9, here we have 5, and we have 2, and here we have 20, and I have 16 and 30. And imagine I am searching for the key 9 here in this tree. So how do we search for the key 9? So imagine that this is, again, it's basically search x and 9. So x is the root of this tree when we call it, and 9 is the value we are searching for. Well, the way that you would search a tree is very simple because we have that very important property on binary search trees, which is that the keys in the left subtree are smaller than the key in the node itself, and the keys in the right subtree are greater than the nodes in, the key in the node itself. So if I'm searching for 9, I need to ask, is 9 smaller than 15, smaller than or equal to 15? Of course, if it's equal to 15, we say yes, it is there, and we are done. But we are asked, is 9 smaller than or equal to 15? The answer is yes. So 9 is smaller than or equal to 15, then we know if 9 is in the tree, it must be in the left subtree. So now we say, okay, go to x dot left. So we go to the left child of x. We come here, we say, is 9 smaller than or equal to 6? The answer is no. Then we know if 9 is in the tree, it must be in the right subtree of 6. Then we come this way. We say, is 9 smaller than or equal to 7? The answer is no. We know it must, if it is in the tree, it must be in the right subtree of 7. So we come, sorry about this. In this case, we come to the right subtree of 7. We ask here, is 9 smaller than or equal to 13? The answer is yes, so we have to go left. I come here and I say, is 9 there? Yes, 9 is there. And I say, yes, return 9. Return that it is found in the tree. Okay, so if it's a Boolean function, we return yes. Or if it's a function that where we need to return a pointer to the node that has that key, we just say return x. Okay, I'm not going to write the pseudocode here, but you get the algorithm is very simple. If you are expecting x and x is nil, or x contains the key that you are searching for, just return that x. Otherwise, if the key in x is greater than the key you're looking for, or the key you're looking for is smaller than the key in x, go left. If the key you're looking for is greater than the key of the node you're looking at, go right. This is all what the algorithm does. You can actually implement it recursively as well. Now, what is the running time of this algorithm? If you look at it, it's not necessarily O of n. I mean, if you look at this tree that I just drew here, and if you look at these nodes, we didn't look at them at all, right? Because when we checked if 9 is smaller than or equal to 6, the answer was no, then therefore we ignored completely the left subtree of 6. The same thing, this subtree was completely ignored. So it's not really O of n. But if you look at it in the worst case, what happens is that we are going to be what I just drew here, we are going to be traversing one terrible path. Terrible as in very long path from the root to a leaf. Now, I had defined the height of a tree. The height of the tree is the length of a longest path from a root to a leaf. In the worst case, the number of operations that we perform is O of H. Okay, so the number of operations we could perform when we are searching for a key is O of H. So for example, for this tree, if I'm searching for the key 15, it's just one operation. I look at the root, I find it, I'm done. But if the element I'm looking for example, let's say is 14, the 14 is going to force me to go through that longest path in the tree to find that it is not there. Okay, so in the worst case, this is worst case running time of search on a binary search tree, it's O of H. Okay, now that H can be on the order of n, that H can be on the order of log n. Okay, so again, if you think, for example, about a balanced tree, something like this structure, if this is the tree structure here, and you think about n, and this is the height of the tree, the height is on the order of log n, where n is the number of nodes in the tree. So this would be good if we can maintain, if we have a binary search tree that is balanced like this, whose height is on the order of log n. This is good, because an alternative, a very bad case, is this kind of tree where h is basically n minus 1, or also in the order of n. Okay, so if we have a tree with 1,000 nodes, if the tree is balanced, we end up doing on the order of 10 operations, and if the tree is not balanced, it's like a chain like this, we end up doing on the order of 1,000 operations. Okay, so the search operation itself, the running time in the worst case is on the order of the height of the tree, which again, depending on the shape of the tree and how things are structured, can be all the way to n, as big as n, order of n, and it can be as small as the order of log n. Of course, we prefer log n, but to maintain log n, we have to impose more properties on binary search trees, which is something we will see later.